you very much. I'd like to thank the organisers a lot for the opportunity to talk about this today. So yet again, another new package code that I'm really happy to present. So our development team for CosmoSIS was made up of Joe Zuntz and Sarah Bridle at the University of Manchester in the UK, Mark Paterno, myself, Scott Dodelson, Saba and Jim at Fermilab, and also Doug Rudd at the University of Chicago. So this code was really a collaboration between astronomers, cosmologists, statisticians, and computer science people, bringing all of these efforts together to build what is CosmoSIS. Okay, so just a little bit of an introduction before I talk about CosmoSIS. The classical estimation problem we have in cosmology is we're trying to make plots like this. Okay, we're interested in certain cosmological parameters, so let's call these parameters theta. And the real thing we want to estimate is the probability of those parameters if you give me some data set. Okay? So generally we think about these parameters as being random variables, and what you're going to do is you're trying to evaluate this probability distribution function, which is called the posterior. And so just using Bayes' theorem, we know that the posterior distribution function, we don't need to evaluate this or know what this is directly. We can use Bayes' theorem. We make some assumption for what the likelihood is, right? So flip things around. If you give me the data, what's the likelihood of the data given a set of parameters times a prior probability in those parameters? So that prior can be something physical, like the matter density in the universe shouldn't be less than 0, or it could be some prior information coming from previous surveys. So generally, we only work out the top line in this equation, and we don't worry too much about the bottom because this is a normalization factor. We know that overall this is a probability, so we don't worry about that. So what we want to do is we want to figure out what the maximum likelihood values are, or the confidence intervals for a set of parameters, right? And this is how we make these plots in cosmology, these 1 and 2 sigma confidence intervals for parameters like omega m and w. And generally, we do this by evaluating the likelihood using some kind of Markov chain Monte Carlo technique, where we move around in parameter space in a clever and efficient way, estimating the likelihood in multi-dimensions and figuring out where the maximum likelihood spot is, where the sweet spot is in parameter space. Okay, so when we think about that's what we're trying to do in cosmology, then what are the problems we're currently facing in cosmology? So currently we have lots and lots of sometimes correlated observables, right? So there's not just one probe we're thinking about. There's lots of different probes. There's the CMB, BAO, lensing, all of these types of things. Clustering supernova. And really, if we want to constrain the parameters to a level of 1 and 2% precision, combining these probes is going to be really necessary. So we can't just look at single probes in isolation. We need to get those joint contour plots. So the likelihood of all that data given a certain set of parameters. And then if we think about all those different observables, each one of those has different theoretical models. And inside each of those theoretical models, what you have are different parameters, not just different cosmological parameter dependencies, but different maybe nuisance parameters or systematic parameters. So these can be different for each of the models, but then they can also be correlated between models. So if you think about things like maybe photo-Z errors, how you model those, if you're looking at combined probes or joint probe constraints, then those systematic errors are going to be correlated. And how do you deal with those in your sampling technique? Then there's also the issue of complicated and possibly multimodal, right? So things are no longer just simple Gaussians, posterior distributions or likelihoods. You have to make some assumption about that likelihood in order to evaluate it in an MCMC chain. Everyone just assumes Gaussian, but we know once we start combining all these probes, the likelihood of it being actually multi-Gaussian is very, very slim. So then how do we move beyond those simple assumptions and fold that into our estimation technique? And then the last problem we face is that currently we're in really, really large collaborations, okay? If you're interested in going after what is dark energy or what is dark matter, you're working with maybe hundreds of thousands of people in these collaborations. How do you track contributions of code amongst each other? How do you ensure reproducibility and consistency if one PhD student is working on a similar project to another? And how do you use the wealth of existing code and data without wasting your entire PhD or postdoc trying to learn a new field, trying to understand someone else's legacy code, right? You don't want to do that. And maybe even learning a new coded language. So maybe you're used to working with Python, but CAM is written in Fortran and you don't want to have to suddenly go off and learn Fortran. So these are a list of some of the issues that we're currently facing in sampling techniques. So CosmoSIS was designed to address each of these issues. So what is CosmoSIS? It's a new cosmological parameter estimation code which basically tries to answer each of those problems that I listed on the previous slide. The difference with this code is the focus on modularity. So breaking up parts of the code into what we're calling different modules, right? So you can have a separate module, which is just a snippet of code, which might either do a likelihood calculation or just a simple physics calculation. CosmoSIS is an open source code which the community is actively contributing to. Okay, we're inviting contributors, and people have contributed several different modules to CosmoSIS, and we've folded them in. At the moment, all of the modules can be written in different languages. We're supporting Python, C++, C, and Fortran. The main code of CosmoSIS is written in Python and C++. And we package CosmoSIS with a choice of physics and likelihood modules, which I'll go into a little bit detail later on. We also package it with a collection of different samplers, which are mostly in Python. So there's not just one MCMC sampler which you can use. You should be trying different ones, because really your cosmological constraints shouldn't change if you change your sampler, and that's kind of a robust test of what you've assumed for your likelihood, something like that. And we also package a nice plotting tools in CosmoSIS for some nice post-processing effects, and those are all written in Python as well. Okay. So I just want to give you an example of, a classical problem of when you would use CosmoSIS and how this was done in the old days and what you should be doing now. So let's say, for example, you work on supernova. That is your area of expertise. But you want to make this plot, which shows joint constraints in the gray contours here from supernova, the Planck likelihood, the WMAP likelihood, and BAO. How much work is involved in this? Okay. So let's just step through what you would need to know given your expertise. Okay. So at the top here, I've written down a simple skeleton of what the log likelihood is for these joint constraints. The first term here is the distance modulus for the supernova bit. That's the part you're the expert in. Then you need to think about maybe this chi-squared term for including the BAO and the CMB constraints from Planck and WMAP. Right? You haven't quite looked into all the dirty details of what the model is there, but we can walk through all the details. So the supernova you understand, right? You can decide on your light curve fitter. There are several different choices for those. Different parameters for each can be varied in this case. And then you need to think about, well, maybe there's different languages that are involved for running a simple likelihood, which is public, so C++ in the case of JLA. Or maybe you want to run some simulations and actually output light curves. If you use SN Cosmo, that's Python. If you use SNANA, that's in C and Fortran, a mix of the two of those. And then maybe you want to change some parameters in this case. How do you incorporate that into a likelihood code which is already public? Maybe you're interested in varying W0 and WA. So this is just some of the things you need to think about for the supernova section alone. The next section to think about is, well, you want to use the WMAP and Planck likelihoods. So now you need to think about, okay, well, what Boltzmann code do I use? There's several out there. There's CAM, class. Maybe you want to think about modified gravity models. There's MGCAM, is it GR? Different parameters for each of these, and each of these are all written in different languages as well. Then you want to look at the likelihood codes themselves. This is just for predicting what the temperature power spectrum is, but for the individual likelihoods, the WMAP likelihood is in Fortran, the Planck likelihood is written in C, and you also have different versions and different nuisance or systematic parameters in each of these public likelihood codes. So you can imagine that this might take another year of your time trying to understand what to do with each of these likelihoods. Then for the final part, for the BAO, you need to estimate several things in this instance. Maybe the two-point correlation function or the power spectrum in Fourier space. You need to think about, well, how do I estimate the actual linear growth rate, or the linear growth rate times sigma 8 at the redshift of the data of the Boss CMAS sample, for example? And then how do you model some systematic effects like the bias? We don't know how the galaxies are actually tracing the underlying dark matter. And also, how do you model the redshift space distortion effects, the peculiar velocities distorting the clustering signal in redshift space? So that's probably another year of work trying to understand that one probe. So after you've pieced all these things together, you still have to maybe write your own sampling algorithm or implement one of the public samplers that is out there. You also need to make sure that the shared cosmological parameters between all of these probes are treated properly in both the likelihood and inside the models in each of the probes. And then you may have shared nuisance parameters between each of these that you need to take into account in your system that you're building. So clearly this looks like an awful lot of work. Okay, so how do we do this in CosmoSIS? Literally, we've set it up so that when you think about each of those different probes, and you think about each of the theoretical models that are needed for each of those probes and each of the likelihoods, then each one of those represents a module inside CosmoSIS. So you really can separate out all the physical calculations, but ensure consistency in how the cosmological parameters and systematic parameters are treated across a pipeline of modules. So what we've set up in CosmoSIS is that it's a config file, which is passed to the main CosmoSIS engine, where you basically separate out a module into pipelines like this. So this is an example in your .ini file, where you list each of the modules. So here this is the exact same example on the previous slide. So the first module here is consistency. This is just making sure that all of the cosmological parameters you've specified are in the ratios that we need them. So for example, if you've specified omega m and h, but CAM needs the combination omega m h squared, consistency just combines these two and makes sure that that parameter is saved in the data block. Next, we run CAM, which is a separate module, the Boltzmann code for outputting the power spectrum, the JLA, the supernova light curve. We also have some Riesedal supernova likelihood here, WMAP shift. This is just a shift parameter from the WMAP data. We also have a Planck likelihood here, a growth function, which calculates the F sigma 8, which you need for the BAO, and then finally some BOSS data for the BAO data here. So all these modules currently exist in CosmoSIS, so you can literally just change that module pipeline, and you've run everything that I showed on the previous slide. Okay. So all of these modules are currently in CosmoSIS. Another nice feature here is, say you don't want to use CAM, say you want to use class, or you want to check, is there any difference between CAM and class? All you have to do is just change that one line in the ini file without recompiling anything, and you can just set your sampler going again. All of the cosmological parameters and shared systematic parameters are consistent across the pipeline. Every single module here reads from a common data block. So there's no misunderstanding between omega matter maybe in different parts of the code. You're also able to set value and prior ranges for each of these parameters. And you can swap in and out these modules with ease. And you can also add in your own modules to this. Okay. So another feature in the ini file is that you can specify the sampler you want. And you can also change that sampler with ease as well, right? Literally just by changing it in the ini file. So we have several different choices. For example, we have multi-nest, and you specify the sampler you want like this. And then the details, individual specifications for the samplers are underneath. We also have some standard samplers, just like in Metropolis Hastings. For the individual modules, right, say you were writing your own module or you wanted to use something like the CAM module, which is in CosmoSIS, you also specify this in the ini file, and there are different settings for each of the modules. So one of the main things is that if it's not in Python, something like CAM, which is in Fortran, CosmoSIS automatically compiles that into a shared library object. So you don't have to worry about this when you make CosmoSIS. This automatically will be done in the make. And then there are different settings. So you can maybe, if you don't want to output the temperature power spectrum, you can just do this in a background only setting. And this is how you can specify the output from each of the different modules. Okay. So here's just an example of some of the modules that we package with CosmoSIS when you download it. So we have several different Boltzmann integrators. So we have CAM, class, HaloFit for a nonlinear matter power spectrum. There's an alternative nonlinear matter power spectrum there, which is updated HaloFit. If you're interested in modified gravity, there's an MG-CAM and an ISIT-GR. We also have some modules for weak lensing and calculating intrinsic alignments. We have lots of likelihood modules now at the moment. So we have WiggleZ, which is a large-scale structure redshift survey, different versions of WMAP. So again, if you wanted to compare, did constraints change between WMAP in different years, literally changing that input in the ini file and the specification of the module is all you need to do, right? You don't need to worry about how CosmoSIS is interacting with that code. Same with the Planck likelihood. We also have likelihoods from BICEP2, BBN, BOSS, DST, lens, cluster masses, and supernova. We have some physics modules which just do physics calculations. So even if you didn't want to do sampling, if you just wanted to calculate things like a mass function or luminosity function, you could run CosmoSIS to do that. You don't need to do any sampling at all. You could just use it as an engine for generating distances in a given cosmology. We have a lot more physics modules which do different calculations, and then some large-scale structure modules that people might be interested in, a power spectrum emulator called Franken-EMU, and also one that calculates the growth rate or growth factor. So as I mentioned before, we also have a lot of different samplers inside CosmoSIS. So here's just some of the really interesting features of alternative samplers. And the reason to think about using many different samplers and not just one is the idea of shielding yourself against maybe your distribution is multimodal and you want to make sure that you're not missing peaks in that distribution, okay? Or maybe you're interested in getting things like the evidence, and some of these samplers won't give you the evidence if you wanted to compare cosmological models. And then the key thing is that your results just shouldn't change, right? When we use these samplers, sometimes it's a bit of a dark art. You know, how long do you run the chains for? How many walkers do you put down? When it's converged? How do we even determine if it's converged, right? And papers can be really sketchy on these details. And that's fair enough, because it is a dark art, right? There is no absolute scale of what it means to be converged. But at least if a paper was to use several of these samplers and show that their results didn't change, then that would be encouraging. Okay. So if you're interested in getting started with CosmoSIS, I'd recommend that you go to our Bitbucket website. So we have quite a developed wiki page here. We have instructions on how to download and install CosmoSIS. It literally is a 4-step install. So the nice computer scientists at Fermilab have made sure that everything is packaged really, really nicely. We use a product called UPS to deliver all the libraries that CosmoSIS needs. So you don't need to worry about installing anything. You don't need to worry about installing FFTW or a GCC, anything like that. Basically, we install all our environment variables with this UPS package. So once it's installed, you can basically try out these demos, and they increase in complexity, starting off with very, very simple examples down to longer demos where you can run much longer chains. Most of the short demos you could just run on your laptop, though. If you're interested in being a developer for CosmoSIS, we really invite contributions to the standard library. So this is where if you have a small piece of code that does a physics calculation, or if you have a likelihood module which you want to include, this would be really great. So what we're advising people to do is that you clone our repro, change it, include your own different module, and then issue a pull request, and our team will evaluate it. So on this website as well, you can sign up to our mailing list if you're interested in getting involved. Okay. So if you want to be a developer, how do you write your new little module that plugs into CosmoSIS, right? So you have your little snippet of physics calculation code. It could be in anything, it could be in Python, C, whatever. Then all you need to do to make it talk to CosmoSIS is write this interface code. So the interface code literally only needs to be 3 functions: a setup function, execute function, and cleanup function. This is particularly nice in Python because in setup, normally you allocate memory for maybe arrays or anything like that, and then in cleanup you have to free these. But if you're working with Python, then setup really, you don't need to do anything here. So the setup function is where you might specify things like outputs that you want. Maybe you only want the power spectrum output at certain redshifts. So these are setup features which exist throughout the entire sampling loop, whereas the execute function is something which actually will be done every single iteration by the sampler. So this is the only thing you need to do in order to make your physics calculation code talk to CosmoSIS. Okay, so we're getting ready for version 1.4 release. We do have bi-weekly development team telecons, so really we're listening to the community, and if anyone has any requests for things that they would like to see in CosmoSIS or extra code they would like to add, these are the things we discuss at our development meeting, and we actively help people add their code into CosmoSIS if you want that help. We've also set up new science telecons where anyone can join in, right, and just listen to what kind of science is being done with CosmoSIS. And if you want to advertise your work, that would be great as well. And another new feature we'll be setting up in the coming months, we'll be emailing people about, is webinars. We'll be setting up online live tutorials really for a range of expertise. If you're a grad student, a postdoc, or faculty, and you want to learn more about sampling procedures and maybe advanced sampling techniques and how to use CosmoSIS, these webinars will be a perfect place to learn about that. Okay, thank you.
What's been your experience with packaging so many different pieces of code and trying to distribute that? And has that been a headache or?
Yeah, it has. Not for me in particular, but for our computer science guys, it's been a headache. So one of the biggest issues we found is supporting this to run on any operating system. And one of the biggest headaches we're running into at the moment is the latest upgrade, so El Capitan. And so basically the way the UPS system works is that we will support certain systems like SL6 and OS, Mac OS systems, but actually making sure that it installs correctly on any operating system, that's been the huge headache because we're installing all our libraries ourselves. And so making sure that that's a uniform experience for everyone. We're also installing matplotlib. I mean, you run into huge issues with people's pre-installation of things.
Would it make sense to use Conda for this?
So we do actually install Conda. The Python packages are installed with Conda.
Oh, so
as
Conda
part
is
of this.
in this.
It's installed in this. So you automatically get Conda with this. So what we're thinking about moving to in the future is this will be installed under a virtual machine on people's laptops. And then that might make it a cleaner environment because we definitely have run into issues with different operating systems.
So maybe we can have one more question and the next speaker can start setting up.
To what extent do you have direct participation from all of the other groups that are providing the different models? I mean, there's a very wide community, giving you each of these different constraints and models, and are they actively involved in this, in the collaboration of CosmoSIS?
No, they're not. So really at the moment, with the core development team, if any code is out there and it's public and we think it will be useful, then we just take that code and we don't really have much interaction with developers in that code. Anyone who approaches us and wants to actively include their code, then we will have a lot of participation and interaction with them until it's installed and until we test it and make sure that it's working and it's doing what it says it should do. Then we interact with them a lot. But once it's inside CosmoSIS, then really we move on and we think about including the next piece of code. I also want to say that CosmoSIS is being used as part of the DES collaboration. So there's a private fork of CosmoSIS, which is, what we're advocating for collaborations going forward is that they use a private fork of this until they want to release their data. And then all the INI files they've used and all the pipelines they've used should also be released with the data. But this is being used actively at the moment in DES. A separate group uses CosmoSIS for all the cosmological analysis.
So much. Thank you, Elise, again.